right, so we're going to work a problem with combustion. We've got methane. It's burned completely with 100% theoretical air, and we're supposed to find the air-fuel ratio, and we also want to find the air-fuel ratio if we combust methane with 150% theoretical air. So I've got my given, my find, any assumptions that I need to make, and I think I'm kind of ready to go. So the first thing I'm going to do is I'm going to handle A. So if I have combustion of methane with 100% theoretical air, my products of combustion are CO2, H2O, and nitrogen. And my job is just to figure out what those coefficients are. And I also need to figure out what the coefficient A sub TH is. So that's my theoretical air. So how many kilomoles of dry air do I need to have with methane to complete this reaction? All right, so I'm going to do a mass balance on each one of those elements. So for carbon, on the left-hand side, I've got 1 carbon, and that's in that methane, the CH4. And then on the right-hand side, the number of carbons that I have is X. So it looks like 1 is equal to X. Pretty simple. And now I'm going to do it for the hydrogen. So on the left-hand side, I've got 4 hydrogen in that methane molecule. And on the right-hand side, well, I've got the only place that hydrogen shows up is in H2O. So I've got a Y in front of the H2O, but I've got a subscript 2 in the H2O. So the number of hydrogen that I have on the right-hand side is actually 2Y. So the balance gives me 4 is equal to 2Y, and of course I can solve for Y is equal to 2. And then for my oxygen, I've got 2 times A sub TH on the left-hand side, and then on the right-hand side, I've got 2 times X, that's in the CO2 molecule, and then I've also got an oxygen in the water molecule, so I've got Y. So the final balanced equation, it's 2 times the theoretical air equals 2X plus Y. And if I plug in my numbers, I should get that I have a theoretical air of 2. And I'm almost done. I just need to solve for what Z is. So on the left-hand side, you see I've got 3.76. There's a 2 subscript in the nitrogen. And then I also noticed that I've multiplied the theoretical air, A sub TH, on the outside of those parentheses. That's multiplying with the molecule, the oxygen molecule and the nitrogen. So I need to take that into consideration. And then on the right-hand side, it's just 2Z. So if I plug in the numbers and solve for Z, I get 7.52. So now I've got the final equation for my combustion of methane with 100% theoretical dry air. And I'm not going to get the air-fuel ratio yet. I'm going to go ahead and handle, while I'm in the mode of balancing equations, I'm going to get the second one. So this one, I've got 150% theoretical air. So I'm multiplying that A sub TH by 1.5. Now that A sub TH is what I just solved for in part A. That's the minimum amount of dry air that I need to have in that combustion reaction with methane in order to have a complete combustion. So I've multiplied the A sub TH by 1.5, and then the other way that this has changed is I've added an oxygen on to the product side. So I do need to resolve for X, Y, Z, and now W on the reactant side, and I'm just going to do another mass balance. So for carbon, I still see that 1 is equal to X. There's 1 carbon in the methane, X carbon in the CO2. For the hydrogen, things still haven't changed. I've got 4 on the left-hand side. I've got 2Y on the right-hand side. Now the oxygen will have changed because I've got a 1.5 in front of the dry air term. So it's going to be, and I got Y is equal to 2 for the hydrogen. So for the oxygen, I've got 1.5 times the theoretical air, which I said was 2. I solved for 2 in part A, times 2, the subscript in the oxygen. And then on the right-hand side, you've got 2X for the CO2. You've got Y for the H2O. And then, of course, you've got 2W for that oxygen term, that 4th term in the product side. So if I plug everything in, I get a W is equal to 1. And then for my nitrogen, same thing. I've got a 1.5 in front of that dry air term, so it's going to be 1.5 times the theoretical air, that's 2, times 3.76 times the subscript 2 on the nitrogen term, equals 2z. And if I solve for z, I get 11.28. So there's my final, almost final balanced equation. There we go. There's my final balanced equation for 150% theoretical air. And let's see, now I'm ready to plug in things for my air-fuel ratio. It's defined as the mass of the air over the mass of the fuel, but I don't have things in terms of mass. What I've got things in terms of are moles. So the number of moles of air is just 2 times 4.76, because the 4.76, that's the number of moles of dry air that I've got in the parentheses of O2 plus 3.76 nitrogen. That's equal to 4.76 kilomoles of dry air. We mentioned that in the lecture for the combustion intro. And the molar mass of the dry air, you can look that up in table A1. And then on the bottom, of course, I've got a 1 in front of that methane. So you've got 1 kilomole of CH4. And then the molar mass of methane, you can find that in table A1. So if I do the math, I ended up getting 17.24 kilograms of dry air per kilogram of methane. And then for the 150% theoretical air, it's the same equation. I've just got a few different coefficients. So it's going to be 3 times 4.76 kilomoles of air. And that's really the only thing that's changed. And so I get a 25.86 kilograms of dry air per kilogram of methane. All right, well, that's it. Thank you very much for watching, and let me know if you have any questions.